Hey everyone, welcome to Structural Engineering Across the Pacific Ocean 2024. I'm Henry Rowden. I'm a structural engineer at Becker in Auckland, New Zealand, and I'm the chair of SESOC Emerging Structural Engineers Group. Unfortunately, my camera's packed in today, so you're unable to see me. Today's webinar is a collaborative event between SESOC's Emerging Structural Engineers Group and the Structural Engineering Association of Northern California, aka SEAONC's Young Members Forum. Some of you may recognize the name of this event. This event was ran for the first time last year with great success, so we've thought about bringing it back again for another go this year. During the webinar, we'll run through some exciting rapid-fire presentations that focus on young engineers tackling complex projects on both sides of the Pacific Ocean in both New Zealand and Northern California. I'd also like to welcome my counterparts in Northern California, Megan and Lauren, who are the chairs of the SEAONC Young Members Forum.
Yep. Hello, everyone. Thank you so much for joining our webinar today. We're really excited to get the opportunity to collaborate with SESOC again this year and are in for some great presentations. So stay tuned. Thanks, Henry.
Thanks, Megan. So the way we're going to run this event is we'll have each of our speakers present and then we'll host a Q&A session at the end. Feel free to drop your questions into the chat throughout the presentations. First up, we have a speaker from SESOC. Chloe Leach is a structural engineer at WSP in Auckland, New Zealand. She was seconded to the City Rail Link project from 2021 to 2023. Chloe joined WSP as a graduate in 2020 and has been working in the Auckland structures team for 4 years. Chloe has experience in the structural design and detailing of new building projects and seismic assessments of existing structures, with a particular interest in major projects. Welcome, Chloe.
Thanks, Henry. So hello, everyone. My name is Chloe Leach, and I'm a structural engineer working for WSP in the Auckland office. And today I'm going to be presenting on the City Rail Link project, specifically Te Waihoretu Station, where I spent just over 1.5 years as part of the design and construction phase services team. First, some background to the City Rail Link. CRL is the largest transport infrastructure project in New Zealand's history and is due to be completed at the end of 2025. When finished, it will connect Auckland's entire rail network with 3.45 kilometre twin tunnels between the redeveloped Waitemata station at the north of Auckland CBD and Maungawhau station. The completed project will also include 2 new underground stations, Te Waihoretu and Karangahape station. The completion of CRL will double the capacity of Auckland's rail network by 2035 with a predicted 54,000 passengers an hour at peak times. Here we have a map of Auckland City where the project is currently taking place.
Hey, Chloe. Sorry, do you mind sharing your screen?
Oh, is it not sharing?
Don't.
Oh. Is that working?
There we go. Thank you.
Oh, sorry, guys. My Zoom's been playing up today. So I'll just start this again. Here we have a map of Auckland City where the project is currently taking place from Te Waihoretu Station to Maungawhau Station along the yellow and orange line is the route which the twin tunnels take. In order to construct this, a tunnel boring machine was used. It first travelled from Maungawhau along through Karangahape and down to Te Waihoretu, completing its first trip at the end of 2021. Before being dismantled and rebuilt to complete the trip again with the final breakthrough at Te Waihoretu in September of 2022. The tunnel boring machine worked by slowly drilling to excavate and remove the soil in its course before placing segmented concrete rings to line the tunnel as it propelled itself forward. During my time with the Link Alliance, I worked on Te Waihoretu Station. Te Waihoretu is a new 20-metre deep and 370-metre long underground station in Auckland's Midtown. And when CRL is open for public use, it will be Auckland's busiest station due to its central city location. The station will have entrances on Victoria Street and Wellesley Street, providing easy access to key Auckland hotspots like the Sky Tower, Civic Theatre, and Aotea Square. Te Waihoretu has also been future-proof for the potential development of a northern line beneath the station. The design and construction of the station has been split into 4 main zones. So moving up the model on screen, starting at the bottom, we have the southern zone, which includes the southern Wellesley Street superstructure and substructure below. Then moving up slightly, we have the central station box zone, which extends up to the Victoria Street entrances, where you can see the box jut out in the model. And then finally past this, we have the northern running tunnels. Breaking that down, the first zone we have is the Wellesley Street superstructure. This building serves as the main station entrance and holds a lot of the back of house plant and machinery. And you can see it with the facade and lights, which recently went up in the picture on screen. The structure is a 4-story reinforced concrete, 2-way moment frame over a 3-story basement substructure. The superstructure has been designed with the capacity to support a future 24-story oversight development building. So we've got some pretty big columns. Then going down to the substructure of the Southern Wellesley Street zone, this is where the entrance connects to the bored twin tunnels, which link Te Waihototu up to Karangahape Station. And you can see in the picture on screen the moment the TBM made its final breakthrough into Wellesley Street. Then moving north from Wellesley Street, we have the central station box. This zone will function as the primary area where commuters will board the trains, as you can see in the architectural render, and this will connect the Wellesley Street and Victoria Street entrances. We've also got to the section of the station which is entirely underground, with the roof slab just under the road level. The structure of the central station box comprises of reinforced concrete diaphragm walls that support suspended floor and roof slabs. The station box has 2 floors. The lowest B4 level will contain the train services and platform, and the upper B1 level is the main concourse for the flow of passengers between the entrances. The construction methodology for the main station box was top-down construction. This involves vertical excavation and installation of diaphragm walls into the soil before constructing and pouring the station box roof on top of the existing soil. The soil below the roof is then excavated out underneath until the required level of the next lowest slab is reached. The slab is then poured and the process continues. And you can see in the photo to the right, the last bit of soil being lifted out of a construction void in the roof before the B1 slab was poured. Moving further north, we have the Victoria Street zone. This is where we have the second set of entrances to the station, one to the east and one to the west. These will be the main pedestrian access points to the station and will lead passengers to the platform via the central zone's concourse level. The eastern entrance is essentially a concrete ramp structure, which flows directly onto the station's concourse, which you can see in that architectural render. And the western entrance consists of a small steel structure with escalators down to the concourse. The construction methodology for this zone was again top-down construction, and you can see in the photo to the right, excavators removing the soil from underneath the Victoria Street roof and taking it out of the future eastern entrance ramp. Also shown in this picture is one of the only 2 central plunge columns used in the station. Essentially, the plunge columns are hollow steel columns with shear studs on the exterior, which are driven into the ground at the same time the diaphragm walls are installed. They're filled with concrete during the roof construction and excavated around. After the soil is removed, the concrete cages are placed around the column and an exterior is poured. Finally, the last zone is the northern running tunnels, which connect Te Waihototu Station to the previously completed cut and cover tunnels running beneath Lower Albert Street and down to Waitemata Station. This section of the station was constructed using a different construction methodology known as cut and cover. And this was due to the really tight constraints in this area, meaning that the plant used to excavate for the diaphragm walls couldn't physically fit. And this is also why we have reinforced concrete pile walls supporting the structure, as you can see in the picture on the left. The cut and cover construction methodology consists of pouring the piles into the ground, then excavating right down to the underside of the B4 base slab before continuing the rest of the construction in a more traditional bottom-up manner by first pouring the base slab, then constructing the tunnel walls, and finally the tunnel box roof. In order to keep the structure stable during construction, due to the large depth of excavation, temporary steel struts were used to prop concrete whalers connected to the piles up, as you can see in both of the photos on screen at different stages of the project. These were incrementally removed as the soil was reinstated following construction of the tunnel roof slabs. Working in the CPS team at Te Waihototu Station provided me with first-hand experience in taking designs from plans to reality. Supporting the construction process on site gave me a practical understanding of how our projects are built. Since moving on from CRL and working on other types of structures, I consistently draw on my on-site experiences to make sure my designs are constructible. The City Rail Link showcases innovative engineering and a collaborative effort reshaping our transport infrastructure and delivering massive value to Auckland. It was a wonderful experience to be part of the team bringing it to life, and I can't wait to see the positive impact it will have on our community. Thanks, everyone.
Awesome. Thanks, Chloe. Next up, we have Rahul Sharma from SEAONC in Northern California. Rahul works at the intersection of analysis and design for both new and existing buildings. He is passionate about developing complex problem-solving skills and generally takes on challenging projects. Rahul also gets involved in several standard committees such as ASCE 7, Seismic Subcommittee, the Building Seismic Safety Council's Provision Update Committee, and the SEAONC and SEOC Seismology Committee. Welcome, Rahul.
Yeah, thanks. Just want to quickly confirm that you can see my screen.
Yes.
Okay, perfect. Well, thanks. I'm glad to be presenting at this event and going up second. I'm going to be presenting on the Tico Sanchez Magnetic Shield Lab, which is a project that I was able to work on. As mentioned before, my name is Rahul Sharma, and I work at Hobak Lewin. So just as an introduction, this was a lab that was built for Professor Sonia Tico Sanchez. It was completed in approximately 2021, maybe 2022. They got a little bit delayed because of COVID. I'll just note that this isn't an actual building. It's a lab inside of a building. It's located in the Mitchell Building at Stanford University. And so you can, my firm was retained as a structural engineer. So on the left-hand side of the screen, you can see a plan of the building. You can see it inside of one of the rooms in the basement of the building. What's in green is the lab, and what's in hatched red is a ramp leading up to the lab, which we also designed. So before I go into the structural engineering, I just wanted to give a quick overview and background of the project and the lab. So I'll start with Professor Sonia Tico Sanchez. This is an image I pulled from the internet. She's an assistant professor at Stanford University, and her field involves studying the magnetic field of rocks, both from Earth and from outer space. And when I asked her how she got into this field, she said she wanted to work into outer space, but she didn't know how to pursue that. So that led to a career in planetary geology and geophysics. And so why is it important to study the magnetic field of rocks? So I'll start with the Earth. The Earth generates these magnetic fields through liquid metal flowing through its interior. And what it essentially does is it blocks harmful solar rays from interacting with the Earth's atmosphere and changing its chemical composition. So essentially, it's necessary for habitable life on Earth. And also another fun fact about it is that you can use this magnetic field to understand the tectonic motion of the Earth's tectonic plates. And so I thought that would be interesting for this group because that relates to earthquakes. Other planets such as Mars have lost their global magnetic field. So that's partly one of the reasons why they're inhabitable. And it's interesting to understand how these habitable environments form because they generally take billions of years to form. So what Professor Sonia Tico Sanchez does is she studies the magnetic field of these rocks, both from Earth and from outer space. So what I have on the screen here is an image of a moon rock that she was showing to me. And essentially, it's important to have a lab that can block out the external magnetic field so that she can solely when she's measuring the magnetic field, it's just solely of the rocks and not the built environment and not the planet around her. And so that's why it was necessary to have this to build this particular lab. This was done through embedding several layers of thin metal sheets into the lab's wall and roof, and then demagnetizing them. There were there's other labs of these constructed at Harvard and Rutgers, but those are both like East Coast schools, and so they didn't have the same seismic criteria. So that was one of the challenges of it's essentially justifying the lateral force resisting system of this particular structure. This was constructed by this contractor, Lodestar Magnetics. That's who we were working with. They were great to work with. And I mean, as far as I know, they're the only ones that construct this type of lab. So going into the structural design, it looks simple, like a box, but it was actually quite complex. The gravity system consisted of built-up box beams and perimeter atypical walls. The lateral system was wood diaphragms and perimeter walls. We designed that per ASC 7, Chapter 13. And one interesting and unique fact about this lab was that all the metals and fasteners had to be non-ferrous because we couldn't have anything interfering with the lab's ability to block out the magnetic field of the built environment. So in terms of the non-ferrous materials for fasteners, we had to specify either aluminum nails or stainless steel screws. For the rebar, which was necessary because they had to construct a part of the ramp out of concrete, and they also dug into the slab and removed some of the slab and replaced it. They had to either use solid round glass fiber reinforced polymer bars or stainless steel deform bars. I didn't know those existed. I wouldn't have known those existed without working on this project. So I put the ASTM requirements up there. So another thing when I was kind of touring the lab that I noticed was there were holes in the lab for basically to pass cords through and whatnot. And so I was wondering if that had effect on the lab to block out external fields. And what I was told was that it had a minimal effect because the location of the holes were in line with the Earth's magnetic field. And so I have Professor Tico Sanchez over here kind of posing for me, showing me what the direction of the magnetic field is in the lab, the Earth's magnetic field is in the lab. As I mentioned before, the gravity system consisted of plywood box beams. Also wouldn't have designed these if it wasn't for this type of projects. Luckily, there's an APA design guide on how to design these kind of members, and you have to check a number of different items. So going into the seismic design of this, I think for most of us that do seismic work, the first thing that you have to do is determine the seismic weight. So we calculated what the weight of the material was and then also the contents inside of it. And so I just have an image of here of some of the contents that was in the lab. It's a pretty small lab, but it's packed with quite a bit of stuff. And then going into the lateral system, you know, essentially following the load path from the diaphragm into the walls. I will mention that it was important in terms of detailing. As I mentioned, most of the time this lab was constructed, it was done in low seismic zones. So we had to ensure that there was adequate lateral shear transfer into the lateral elements. Also, another thing I would note is that because there were layers of metal that were embedded in the wall, there had to be a very intricate and unique screw pattern, as you can see on the detail on the right, in order to make sure that everything was intact together. And in terms of transferring the force into the ground, we calculated that there was no overturning for the lab. And so in order to resist sliding, we had these essentially snubbers on each side, which were made of stainless steel angles. And you can see the detail on the left-hand side and an image of it on the right-hand side. So that's kind of my summary of the structural design of this structure. So, I mean, maybe the next question you might ask is what's going on over there now? So Professor Tico Sanchez, she has a student that's studying a lunar meteoroid, which is a moon rock which broke off the moon and landed on Earth. And she's trying to understand how its impact history affects its magnetization. So that's the end of my presentation. I wasn't able to make it down there during construction, but Professor Tico Sanchez was really grateful, really helpful, and she gave me a tour and answered any of the questions I had after the lab was built. So this is an image, a selfie of me and her in front of the lab. Yep. And
Awesome.
That's it. Yeah.
Thanks, Rahul. Next up, we have Jack Southey. Jack Southey is a structural engineer at Becker in Auckland, New Zealand. After graduating from the University of Auckland in 2021, Jack has been involved through the construction monitoring of several different existing building retrofits and redevelopments. Welcome, Jack.
Awesome. Hey, thanks, Henry. Hello to everyone online. Yeah, as Henry said, my name's Jack. I'm a structural engineer at Becker, working in our Tamaki Makaurau Auckland office. And for the past 20 months or so, I've been fortunate enough to work on one of the University of Auckland's heritage buildings called Old Coral Hall. So I'll start with a bit of a look through on the history of this building, mostly because I'm really passionate about it, but also because I think it provides some useful context as to why what we did was beneficial. Before talking through the dilemma of existing ASDRONs and existing as-builts and the sort of troubles that you get with existing buildings, before finally talking about some of the reality capture and information management techniques that we use. So kicking off with the history of Old Coral Hall. So for those that are unfamiliar with Auckland, the Sky Tower is just out of view and sort of like the top left over there. But this is essentially the city campus for the University of Auckland. The Heritage Precinct is that on the top right-hand side. So Old Government House is where government was in between being in Korerakia and Wellington, where it is now for a couple of years. It's an area of fairly high significance, and that's where this building is situated. So the building had a bit of a rocky start, to say the least. So it was first built in 1868, which for New Zealand context is relatively old. But then it was burnt down in an arson shortly afterwards. So as you do, they built a second one. Unfortunately, they didn't learn from the first one, and they built it from timber again, and it was burnt down in arson yet again by allegedly the same person before we landed on what is mostly the building that is there today, the 1872 hall. The building has changed a lot though over the years. So in the top left is kind of that Coral Hall. It was used by the Auckland Coral Society and hosted functions and gatherings, and actually had the graduation for Kate Edger, who's the first woman in a British Commonwealth to graduate with a university level degree. More towards the right, you could see kind of what happened when the university purchased this building. So they built dedicated physics and biology labs on the side. And in the bottom right was what happened shortly after the 1930s Hawke's Bay Napier earthquakes in New Zealand. We found that the front of buildings tend to fall off, and that's not particularly great. So we just did that job for them in a controlled manner. And unfortunately, the portico, which is this brilliant piece of structure up on the top, never made its way back until now. So this is what the building was looking like just before we started construction. Here's a render done by people more talented than me. And this is sort of what we're ending on. So behind those walls is obviously a lot more happening, but on the outside, we're restoring the portico, which is a fantastic accomplishment in heritage restoration, not just conservation, and a pretty cool job to be a part of. But as you could sort of get a feel for from the photos beforehand, the building's pretty bitsy. And I think that's most aptly summarized by a seismic assessment which was done in the 1970s. And with this line that reads, such a catalogue of shortcomings would seem to imply that the building has nothing wrong with it that a well-driven bulldozer could not rectify. That statement probably could apply to a lot of existing buildings out there, but unfortunately this one has heritage protections, or fortunately, I guess. So getting onto the dilemma of existing as drawn and as built, really what I'm talking about here is site validation. And without dumbing it down too much, when we're drawing an existing structure, we're concerned about sort of where it is, what it is, and how intact it is. And finding out all those things all takes time. During design, it's quite hard to get access to buildings, be it there's operational restrictions because the building needs to be accessible. There might be asbestos, or there probably is asbestos. And so there's only so much that you can de-risk on the design side of things. So we end up with, and I'm not saying that this is the silver bullet, but it is a contractor to confirm on site or a design team to confirm on site responsibility. To give some examples of those, anyone that's worked on existing buildings will know that the foundations are always higher than you want them by like a lot. An example of that is, as you can see here, we thought our brick foundations were quite a bit lower. Turns out that they're generally just put on the ground. So there's a fair amount of relitigation of design involved in that. Floors seem to have all sorts of things underneath them. So in this case, once we demolished our existing concrete and timber floor, we found a well underneath it, which is not really something that you have on your bingo card, but fortunately, we're in the process of being able to celebrate that structure in a pretty cool way. So blessing and a curse. But there's also smaller scale things. There's things like where we've got carbon fiber, so we're using a lot of FRP to strengthen our concrete diaphragms. We've then found that that's sometimes in the way of our strands or columns that are just smaller than we want them to be, things that are kind of bitsy and hard to track. This one I've also just thrown in there, another condition thing. Piles back in the 1870s were a little bit different to how we'd have them now. So a lot of things that are all over the place, which is where I lead into with this reality capture and information management piece. So reality capture, when we're talking about that, is anything from sort of taking photos on your phones through to taking a big old 3D model of a building, which is actually what we ended up doing in this instance. So it's not a typical one. Here's a section that was cut through. It's not a cadastral survey in the survey sense where you'd actually build off this. This was me walking around with a Leica BLK scanner, which we have access to here at Becker, and I'm doing my best to try and build a model. As you can see, just looking through this section, immediately it makes it a whole lot nicer to be able to see where our levels are and to see what's sitting on top of the other. There's some other nice renders here, sort of showing what that looks like and being able to digest the structure in a much more palatable format, which is cool. The other thing is we can do successive scans. So in this case, you're seeing this lovely bit of entablature, it's called, which we didn't expect to be there on the side, which is always fun. So we ended up adding some steel work, or not adding, we had to rearrange the steel work to be sympathetic towards that. So it's cool to see how that progresses. Now looking at, information management. So information management is really just the way that we communicate information, and it's anything that's as basic as drawings, which obviously have come a long way over the past 100 years, through to folder structures, which seem to, over the past few years, not gone that far, other than now being a bit cloud-based. So how do we combine the two of them? Well, really, to get the most out of something like a point cloud scan, it does need to be in a format that's actually shareable and accessible. And the same with drawings and things like that. So one thing that we found was really beneficial for us on site was leveraging cloud-based drawings. So we've been using Autodesk Construction Cloud Build, which then we can essentially have a live view of the drawings with hyperlinks to our cans and photos and bits and pieces on it, which has proved incredibly beneficial. We can also then put the scans that I was talking about on this platform. Generally 3D scans and bits and pieces like that have monstrous file types, and you need 5 different programs to be able to open and process them. Being able to have it on a web-based platform and sharing that not just with us but with the architects and with the contractors has really helped to expedite some of the back and forth that's otherwise required with reassessing designs when we find that the existing structure isn't as we want. And then another element of that is I guess augmenting structures onto reality. So it's another step beyond that, where we've found that taking shop drawings and putting them into the real space makes it a lot easier to, and it's not a perfect science by any stretch, but it allows us to kind of de-risk a little bit further where we may or may not see clashes. So the big lessons there really, I guess, are that no amount of intrusive investigation will eliminate the risk of unknowns. You can do your best, but by the time you're digging up foundations and all the rest of it, there will be discoveries on site. So to go about that, having a shared platform for accessing and collaborating on your drawings, your documentation, and your models and the likes thereof is really critical when you're sort of on site, and time is a bit more important than what it might be when you're back in the design office. And I would encourage you all to look at different ways of recording site observations, of engaging with reality capture. It's not just normal photos, 360 photos, videos, photogrammetry, and LiDAR scans have all been really valuable for us. And then the big value out of all of that is that essentially we can just coordinate between us and the contractors, and it breaks down a lot of the communication that otherwise would potentially fail if we're not working off the same drawings and looking at the same models. So yeah, that's it from me. I'll hand it back to Henry.
Awesome, Jack. Thanks for that. Good presentation. Next up, we have Morgan McBain from Northern California. Morgan McBain is a graduate student at Stanford University, pursuing a PhD in structural engineering with a focus on sustainable and resilient structural design. Morgan is working under Barbara Simpson and intends to focus her research on design and optimization of mass timber rocking wall lateral systems for both sustainability and functional recovery criteria. This research will provide a meaningful roadmap for practicing engineers to optimize structural designs for both minimal environmental impact and community resilience objectives. Welcome, Morgan.
Thank you, Henry. Like Henry said, I'm Morgan McBain. I'm a graduate student at Stanford working with Barbara Simpson, and I'm going to talk to you all today about shake table testing of a 6-story mass timber rocking wall building that we completed in San Diego this past fall. I also want to just start by saying this work was not solely completed by myself. So you see a long list of primary investigators, student investigators, and then also industry collaborators that were working with us. So this work is part of a broader Meharry Converging Design Test Program. I have the QR code linked here if you want to look at our website a bit more, but the program overall has focused on testing resilient lateral systems for mass timber structures. We started first with deconstruction of the top 4 stories of the Meharry Tallwood project. So the Tallwood team had tested a 10-story building. We took off the top 4 stories to leave us with a 6-story test specimen. We then first tested mass timber rocking walls with U-shaped flexural plates as energy dissipators, swapped out the lateral system for our second phase of testing, looking at mass timber rocking walls with buckling restrained boundary elements, which are the same as buckling restrained braces, just placed vertically in this case, using those as energy dissipators. And then that's what my work has focused on and what I'll be talking about today. And then our third phase of testing worked on looking at a resilient steel frame, which was developed by Simpson Strong-Tie. So now I want to break down what is this mass timber rocking wall. We start with a mass ply panel, which is a mass timber product consisting of layers of plywood laminated together. And that wall is designed to remain elastic up to the highest considered levels of shaking. And that elastic stiff wall distributes drifts more uniformly along the height of the building. It spans the whole height of the structure. But that even distribution of drift does come with near elastic higher mode effects that can be induced. We then add post-tensioning rods, which also span the full height of the building, also designed to remain elastic at the highest levels of shaking. And those are in place to limit the post-earthquake residual drifts. They recenter the structure after shaking. And then we include these buckling restraining boundary elements at the base to both resist the overturning moment and dissipate energy in the system. And then what allows us to rock is the uplift mechanism. So the wall itself is not directly connected to the base. So we're able to have uplift and rocking, which does result in some compression of the wall toe, but overall does not damage the wall. So this is that wall in the test specimen at the shake table site at the University of San Diego. And if we look at the base of the wall again, you can see the post-tensioning rods that run all the way up the height of the building, as well as the BRBs. And with this test, we really wanted to focus on these key performance properties, which were the limitation of the post-earthquake residual drifts, a near uniform story drift distribution, and any near elastic higher mode effects that might be induced. So to target those items, we conducted a test program where we ran 23 tests. They ranged from 0.1 to 1.1 MCER intensity for a hypothetical Seattle site. And we chose Northridge, Niigata, Ferndale, and Maule records to be representative of 3 different source types: crustal, interslab, and interface. And then you can see on this plot on the right that we scaled them to match the design MCER response spectra, especially focusing on matching the first mode period and the second and third higher mode periods as well. And this video shows one of those 23 tests. It won't let the whole thing play, but just so you get an idea of what we're looking at, this is a 100% MCE intensity for the Northridge ground motion. So you'll see as it starts, the shake table at the base of the building is moving. And then we start to see the uplift of the rocking wall in the somewhat linear displacement profile that we're looking for. And when we test it, so on that building that was shaking, we had right around 600 active sensors. Those are accelerometers, displacement transducers, and some different strain gauges as well. And so from that, I'm going to show just the global responses of the structure that we've looked at so far, starting with the peak relative floor displacements here. So what this plot is showing along the x-axis, we have each test, and then this is the maximum peak relative floor displacement relative to the ground that we're observing in each test. And I'm pulling this from 2 different accelerometers that were at the center of mass at each level, as well as string pots that were connected to the fixed safety towers besides the building. And so what you can see here, we're getting at our highest intensities of shaking, roughly 15 inches of roof displacement. That corresponds to a 1.8% roof drift ratio for this building. And then if we want to take a look more at what's behind that maximum response plot, we can see here for the 0.1 MCE and 1.1 MCE intensities for the Northridge ground motion. We do get near linear profiles, and that corresponds to the somewhat even distribution of story drift that we are expecting. You'll see a couple of the discontinuous lines here. Those are just due to bad sensors. So it's where we are missing some data, but overall, really happy with these results. And then for the accelerations that we observed, again, pulling from those 2 different accelerometers at the center of mass at each level, we got maximum peak absolute accelerations around 1.25 to 1.5 G at the MCE level. And then I will zoom in on the 1.1 MCE Northridge response in this next slide. And what you can see here is we do see some of the higher mode contributions. So rather than having a linear acceleration profile, we're getting the belly and kind of the width at the top, which is important for us to further quantify so that in design of these structures, we can consider those higher accelerations. And then again, here, just zooming in on the response history record, you'll see the higher second mode content oscillations show up in that 0.25, 0.3 second range. In addition to the sensor measurements, we were conducting damage observations throughout the testing program, especially after large shakes. And what we saw was that permanent damage in the structural system was limited to deformation in the BRBs, which was what we expected. So we get about a ½ inch of permanent elongation at the end of testing, but the rest of the structural system wasn't damaged, remained fully intact, which is good. When we're thinking about functional recovery after events, it would be pretty easy to reoccupy quickly. So with that, I just want to look at a couple key conclusions. First, this test has shown that the mass timber self-centering rocking walls with BRBs as energy dissipators are a feasible low damage lateral system solution. We saw near linear floor displacement distributions, which were paired with the near elastic higher mode effects. But overall, the structural damage was limited to the permanent deformation in the BRBs, and the structure was able to self-center with the PET rods resisting any yielding. So with that, I thank you for your time, and also want to thank here a lot of our sponsors. Like I said, this was the work of many academic institutions, as well as industry collaborators coming together. So a big thank you to our sponsors and all of those involved.
Awesome. Thanks, Morgan. Now, last but not least, we have Kane Stratford from Christchurch, New Zealand. Kane is a structural engineer at Oricon with 2.5 years of experience, specialising in the seismic design and assessment of structures. He graduated from the University of Canterbury in 2023 with a PhD in earthquake engineering, where his research focused on the application of non-metallic reinforcement materials in concrete bridge piers as an alternative to conventional steel. During his time at Oricon, Kane has been involved in the structural design and seismic assessment of several mid-rise buildings throughout New Zealand. Welcome, Kane.
Awesome. Thank you for the introduction, Henry. Can I just confirm my slides and audio are good to go?
Yep, looks good.
Perfect. So as Henry mentioned, my name is Kane and I'm a structural engineer for Oricon. And today I'm going to be giving a brief overview of Tupuarangi, which is a pretty exciting project that we've been working on here at Oricon over the last 8 months or so. So this facility is a 7 to 8 story student accommodation building that when completed will host over 280 beds for the University of Canterbury in Christchurch, New Zealand. So the project is being led by South Base Construction in a design and build contract and has a target opening date of January 2026 for the intake of students in that academic year. Just to note, this building is currently in the detailed design phase, so I don't have the beautiful pictures that you've seen in previous presentations, but I will try and make the most out of 3D models and renders to keep things interesting as I take you through an overview of the project. So the University of Canterbury's main campus is situated in the Christchurch suburb of Ilam. And for those who are international listeners, I've provided a small map on the bottom right just to show where we are in context of New Zealand. So the university has experienced a significant rise in demand for on-site student accommodation in recent years. So to meet these growing demands and future-proof the campus for further growth, they've been focusing their efforts on development of new building stock that can supplement their existing accommodation halls. So the proposed site for Tupuarangi is located a short 10-minute walk from the main campus and is bordered on the north and east by the heritage boundary of Ilam Gardens. So it's a pretty quiet and peaceful setting for accommodation. Directly to the west of the site is a 5-story Tupuanuku Hall of Residence that was recently constructed in 2020, of which Oricon were also the structural designers. The building configuration consists of 3 seismically separate structures, including a west tower, which is 8 stories tall and fairly regular in shape, an east tower, which is 7 stories tall and characterized by a 17-degree kink in plan, and connecting the 2 towers is a 7-story central link building. So overall, the facility will be able to cater for a total of 283 students throughout the academic year, of which 270 of these are typical bedrooms, and the remaining 13 are accessible bedrooms, which are spread throughout the building. A rather unique aspect of this facility is that each student gets their own ensuite bathroom, which come in the form of pods that are prefabricated and then lifted into the structure. In terms of functionality, the ground floor of the West Tower is the primary open plan area of the building, with a kitchen, a dining and social space, and several shared student areas, while the ground floor of the Eastern Tower is primarily used for bedrooms and a study area in the single-story extension. As we go up to typical floors, the building use is dominated by bedrooms, except for a shared lounge space on each floor of the central link. The facade system is generally a lightweight curtain wall, however the central link does have some areas of timber infill rain screening. And we do have 2 enclosed plant rooms that are located on the roof of the towers that house air handling units. Now looking at the structure itself, the gravity system is consistent throughout all 3 of the buildings and consists of structural steel framing supporting precast flat slab flooring units with the cast in situ topping slab. So this type of flooring system was selected for its inherent fire resistance, acoustic performance and vibration properties, as well as being easy to erect. 2 unique aspects of the gravity system are a 2.5 meter cantilever portion of the structure on the southern end of the West Tower. And we also have a few fairly significant transfer beams at the first suspended floor of the West Tower, which were introduced to reduce the number of ground floor columns and create an open plan feel that the architect required. The lateral load resisting system for the building is a combination of D-braced eccentrically braced frames, or EBFs, and steel moment resisting frames. These systems were designed just using an equivalent static approach. However, the response was further verified using a response spectrum analysis and in some cases a nonlinear pushover analysis. So both the west and east towers utilize EBFs in the transverse or short direction, which have been configured as regular as possible throughout the length of the towers, while still satisfying architectural constraints. In the longitudinal direction, symmetric moment resisting frames have been used, which I've only shown on one side of each tower here for clarity. To minimize the effects of bidirectional overstrength demands on the corner columns, MRF beams have been pinned out, or a pin connection used where they connect to columns of orthogonal EBFs, resulting in significant savings in both column section requirements and demands on the piles. And finally, the smaller central link building, which is rectangular and very regular, utilizes one-way moment resisting frames in each orthogonal direction. And a similar approach has been used for pinning out MRF beams where they connect to the minor axis of shared corner columns. The primary columns are made continuous at roof level of all buildings and cantilever to support the lightweight roof structure and plant rooms, while the plant rooms themselves rely on a combination of moment frames and bracing systems to resist lateral load. Now the buildings are founded on a grillage of reinforced concrete ground beams on unimproved ground and around 96 screw piles that extend up to 23 meters to the underlying rickety and gravels. All elements of the foundation system have been capacity designed to resist the full overstrength demands from the superstructure. The screw piles do support significant compression and uplift demands in the east-west direction, as the building height to width ratio is relatively large, and they also do help control building settlements under serviceability loads. So beneath the D-brace DBFs, larger ground beams are used to distribute the big push-pull demands from internal columns out to the grouped piles at each end of the ground beam. This has the benefit of providing a larger lever arm to control building deflections and also utilizes the piles in a more efficient manner. So the ground floor slab is tied into the supporting ground beams to act as a diaphragm between brace bays in the east-west direction, and is also designed as a two-way suspended slab between screw piles in the event of settlement during liquefaction. And finally, the base shear takeout is achieved through a combination of shear in the screw piles and passive earth pressure on the face of the ground beams. As we come to the end of the presentation, I'd like to briefly acknowledge the other members of the design and build team. The University of Canterbury and Cedar Pacific as the ultimate and end client, respectively. South Base is the general contractor, and Jasmax as the architects. Here at Oricon, we've been undertaking the structural, civil, and seismic restraint design. And lastly, NGO, GHD, and Pal Fenwick as the design consultants for geotech, fire, and building services. And lastly, just a thank you to all of my colleagues here at Oricon, who names are too many to list, that have been working on the delivery of Tupuarangi so far. Thank you.
Awesome. Thanks, Kane. I guess now we'll move into Q&A. If I could ask all the presenters to turn their screens back on. So I guess first I'll pose a question to Chloe. For the CRL project, what do you think your biggest challenge was throughout the project?
Yeah, I'd say the biggest challenge I found was definitely the tight time frame we had for getting sections of construction done. Because CRL is an alliance, it wasn't just the construction team that were responsible for getting everything built, it was all of us. So we really had to work hard to collaborate, and when there was issues on site or value engineering that needed to be done, it was all of us working together to get things pushed through by the dates that it needed to happen. So yeah, I'd say that was the biggest challenge.
Awesome. Thanks, Chloe. Just a reminder to everyone watching, feel free to submit your questions down below. Looks like we've got one from Danny. Question for Jack. When setting up the 3D model scans, did it require a lot of technical assistance / investment? Like, would it be feasible for a grad to start that and initiate it themselves?
Hey, Danny. I definitely think so. So I only recently, not a graduate through the Beck, I only started about 2.5 years ago. And yeah, basically was lucky enough to get relatively free rein where I was handed the scanner, spent a bit of time looking through YouTube videos and our own internal resources on how to use it, and then spent probably a day at the time walking around site doing our first scan, and then actually registering it on my own on my computer. Hence the big preface that it's not a surveyor scan, it's a sort of someone that's pretending that they're knowing what they're doing, but still ultimately a really powerful tool. And there wasn't, not the astronomical cost that are otherwise associated with getting a total station out to site and the rest of it. So yeah, totally something that is suitable for entry to graduate level engineers.
Thanks, Jack. I guess, Morgan, in terms of the mass timber rocking shear walls, what do you see the biggest issue being with that kind of system? Obviously, it's very interesting. I mean, quite a complex system. What do you see the biggest issue being with this kind of system?
Yeah, I think the biggest challenge right now is getting it into design codes. So it's really not a super complex system in that it's 3 components and it was pretty easy to construct. But there aren't codes in place right now to support design of those systems. So I think that's a big challenge. And then the second thing would be just integration with architects. We were just looking at a structural system for the test specimen, but having the wall go the full height of the building in that way and then tying it into the diaphragm can be a bit challenging. So making that work with an architecture program something that would have to happen pretty upfront, I think.
Cool. Kane, I guess for your building, you've got it on screw piles. It's quite a tall building. At what kind of stage did you bring the piling subby on board to ensure that you could actually use screw piles to take your base shear out?
Yeah, so we were pretty lucky in this project that we had Tupua Nuku, which is the student accommodation building directly next door that used a similar system as well, similar foundation system. So we had kind of that up our sleeve from the start. But Rivex, who are pile designers, were brought on as early as the end of preliminary design is when we started giving them our pile loads for design. So been working on a pretty tight time frame for this project, and there has been a lot of pretty early coordination to get things over the line here.
Cool, thanks, Kane. There was actually a follow-up question. For UC accommodation, is it okay to consider passive earth pressure? I guess soil is okay, not clay. How about the possibility of future excavation around the building?
Yeah, so the foundations are being, or the ground is being fully cut down to the bottom of the ground beams, and then being replaced with hardfill. So we are relying on compacted hardfill to develop that passive soil pressure. Second part of that question is an interesting one. I guess, yeah, I haven't really thought about that. Probably something interesting to to put on the notes, on the drawing notes about no excavations around the building.
Thanks, Kane. For Morgan, are you planning on doing further testing for similar mass timber products on different size buildings?
Yeah, so there's actually been, like I mentioned, I guess there was the Neri Tallwood team. So that was a similar system, different energy dissipators, and that was a 10-story building. And then there was previously a static or pseudostatic test done at Oregon State University, not a shake table test, but still a similar kind of structure. So we now have data points for a 3-story, 6-story, and then similar 10-story structure. So that should be enough at this point for us to refine the numerical models and then create different archetype numerical buildings for any sort of further testing would be simulated.
Mm-hmm. Thanks, Morgan. Jack, about how many scans did you need to take throughout the building to get that resolution in your model? And what is the approximate square footage of the building?
So we had just shy of 300 scans in the building in total, which is yeah, quite extensive. We recently got the more modern Gen 2 BLK, which meant that we were able to complete the scans much faster, and that made a world of difference. And now that I've pulled up my unit converter, we're looking at about 50,000 square foot, so somewhere in the neighborhood of 5,000 square meters. So not a massive building. It's only about 2 stories. There's some mezzanine levels that could qualify as 3. So not a massive footprint, but yeah.
Cool. Thanks, Jack. We're getting close to 1 p.m. here in New Zealand, so I think I'll call it there. Thanks for attending, everyone. Thanks to the presenters. Hope you enjoyed. We'd love to conduct more of these types of presentations in the future. So if you're interested in being a future presenter or being involved somehow, please email us at ese-chair@seasoc.org.nz. I'll put that in the chat, and also if you search up SESOC Emerging Structural Engineers on Google, click on the first link, you'll be able to find a link to the email. Thanks for that, guys. Appreciate it.